I'm the Executive Director of Linux International and the President of Project Hall1. Today we're going to talk about how to make your software perform and how to optimize the GNU Linux code, with a subtitle of We're Not Programming in 1969 Anymore. Now, some of you will say, who is this old guy up on the board who looks a lot like Santa Claus giving away free software? Ho, ho, ho. Well, I started programming in 1969. That was before there was anything called computer science. We were doing computer black magic. And I started off as being an electrical engineer. And I worked on large mainframe computers for 5 years. And then I went and learned Unix in 1980. And I met Linus Torvalds in 1994 and saw Linux for the first time. I've worked for a large number of companies of different sizes. I have done a large number of jobs, being a programmer and a systems administrator and a variety of other things. But most importantly, I've been a customer looking for the answer and for the performance of software, and I've been a vendor trying to create that. So I've been in a lot of the places that you have been. In May of 1994, I met Linus Torvalds. I saw Linux for the first time. And I said to myself, this is something more than a hobbyist toy. This is something more than an educational thing. This has commercial value for the marketplace. And I gave Linus Torvalds his first alpha processor so he could make Linux 64-bit. And in 1995, I became the Executive Director of Linux International. And since that time, I've been going around the world telling people and governments why they should be using free software. To save money, to make money, and to be able to say, to have the confidence that they can make the software do what their country and their companies need. Now, recently, I do all of that work for free. I do not charge for any of that. The way I make my money is by doing consulting. And I'm doing a project now for a company called Linaro. Now, most of you have at least one of these cell phones. And knowing you, you probably have 2 or 3. It is very likely that the CPU of this cell phone is an ARM processor made by the company ARM. But ARM does not make any of their processors. They only design them. And companies like Samsung and Hitachi and a variety of other companies actually produce the processor, or maybe the GPU, or maybe a system on a chip. And all of these companies were trying to put Linux on top of their CPUs, and they're creating a huge problem for the Linux community, with all of these people basically trying to do the same thing. Get Linux work well on an ARM processor. And so a friend of mine decided to start an organization called Linaro. And each of these companies contributes 2 engineers and some money to Linaro. And Linaro makes Linux work well on an ARM processor. But there's a problem, a slight problem. Recently we found out that there's about 1,400 programs inside of GNU Linux that have assembly language in them. And we'll see where this is a problem later on. But we have to fix this problem. Now, I've been in the computer industry for a long time. Some of you may have heard some statements from people in the past, like Tom Watson of IBM, who said, we will only need 5 computers to do the world's processing. Or Bill Gates supposedly said one time that we only need 600K of memory. Who would need anything more? But so all these times, people have been saying these things and have underestimated how much we actually need computers for. I have a friend of mine who has a very famous TV show who once said to me, "Maddog, CPUs are fast enough." I said, "Really?" I've been hearing that for 30 years, and each year it's fast enough. But we have more and more speed. We have this idea of performance. Java is the only language we need. That's not true. We need lots of other ones because I would not want to write my real-time application in Java. I would not want to write it in any language which does garbage collection because my nuclear power plant might melt by the time the garbage collection is finished. I need to write that type of an application with a language like C or perhaps assembly language. Another thing that people say is that nobody needs assembly language anymore. I've seen universities tell me we don't need to teach assembly language because everybody writes things in Java. But you need to know assembly language. You need to know how the computer works. And I've had professors at universities tell me that virtual machines hide all of that. And levels of abstraction hide all of that. And the student doesn't need to know that information anymore. And I come back to these people and I tell them that I work on what I call real problems. When I do my consulting, I do real problems. Real problems use petabytes of data. Real problems need to be solved in milliseconds of time. You don't have another hour for something to be done. If it's not done in the next few milliseconds, it's too late. You don't get another chance. One time I was talking with Linus on the telephone. I said, "Linus, it'd be nice if the kernel had better soft real time." He goes, "What do you mean? It has good soft real time." I said, "How could you say that?" He says, "Well, when I'm playing Quake and the monster has a gun in his hand, I can hit the key and kill the monster. That's real time." I said, "Linus, put a real gun in the monster's hand and see if you can say the same thing." He thinks for a couple seconds and he goes, "Okay, I understand." And the next version of the kernel had much better soft real time. These are real problems. Cell phone applications. You say, "Oh, my cell phone application is fast enough." But what if you want to have better battery life? You want your cell phone application to be more efficient. So it uses less CPU. So it can allow the operating system to go into a quiescent state and allow you to save battery. Because in your cell phone, it's not only the speed at which something is done, it's how much battery does it use. And so you want performance in your cell phone to equate to battery life. And we want to save the environment because it's not only true of cell phones. Google wants to have efficient software because if their software can be 10% more efficient, it means they need 10% more servers or fewer servers. They use 10% less electricity, 10% less cooling, and this saves them real money. So in their case, performance is not necessarily the speed at which the process is done, but the efficiency at which it uses. And we have new and easily affordable devices these days. It's not only the complicated instruction set of Intel or AMD, or even the RISC instruction set of ARM. But we now have field programmable gate arrays, which are available to us at a very low price. Digital signal processing chips, which we can then utilize to do our efficient processing of our data. These are things which are not taught in most schools. How do you use these types of things? And this is the type of thing that we should know as we go into the 21st century. So these are the type of things we should talk about when we talk about performance. How do we use these things in GNU Linux? As I said, I started programming in 1969. My first language was Fortran, but my second language was assembler language for the PDP-8 computer. It only had 4,000 12-bit words of memory, and yet we could do real work on these computers. I learned to program from reading a book and practicing, and so I know that people can do that. Nobody told me that assembly language was difficult. I just picked up the book and started. And this is the way I believe that many people should learn. Because I've been told by many people, and I've experienced this myself, the way that you learn to be a good programmer is to look at the code of other really good programmers and see how they did it, study what they do, and then expand upon that. And that means you also need to be able to understand machine language and how the machine actually works. Now, when I started programming after I left university, I was working for a very large insurance company, and they used IBM systems. These IBM systems cost many millions of dollars, but they only executed instructions at about 100,000 instructions a second. Not millions, not billions. Their memories were very small compared to our laptops of today. One day I was sitting in my office, and this person who was a COBOL programmer came to me and said, "Maddog, I've looked at the source code of my program. I can't figure out what I'm doing wrong." So I looked at their source code. I said, "I can't see what you're doing wrong either. I think that the compiler has made an error." And he went, "What? The compiler making an error?" I said, "Yes. The compiler was written by a programmer like you. And like you, they may have come in on a Monday morning, hungover from drinking, tired from the weekend, not having had enough sex, and they made a mistake. And the compiler is making that mistake right now." So we generated the machine language for the instructions, and we saw the place that the compiler was generating the wrong instructions. That COBOL programmer could have spent the rest of his life looking at his source code and not being able to figure out what was wrong. He didn't know assembler language. He was helpless. I had another time where my boss came to me and said, "There's this program running on the system, and it's running very slow. And not only is it running slow, but when it starts running, every other program on the system slows down. Not only that, but every program on every mainframe, even remotely connected to that one, slows down." Says, "Could you look at this?" So I profiled the program. I ran another program with it that looked at how long every instruction was taking. And one machine language instruction was taking 99% of the program's runtime. I said, "What instruction is that?" The instruction was, read the clock. Seems like a simple thing, right? Read the clock. I could do that by pushing the button on my cell phone. There it is. There's a time. Read the clock. Very simple. But this particular instruction was used by the IBM to control all the other systems, to be able to set up a lock to keep the other CPUs from interfering with it. And so when you executed this instruction, all of your I/O came to a halt. All of your buffers had to be flushed. All of your cache had to be put out the memory. All of your CPU registers were emptied, and then you read the clock. So I asked the programmer, why are you executing this instruction hundreds of thousands of times during your program? He says, I wanted to find out what day it was. Okay. Could you run the instruction one time and store it in a variable? Oh, yes, I could do that. And then his program ran so quickly that the operators thought it had failed. This programmer did not understand the way the machine worked. And he used the instruction without knowing what it did. I had another friend named David Mossberger Tang. And when we did the Alpha Linux project, he wanted to be able to have really large arrays multiplied together. You remember I said earlier, I'm only interested in real data, petabytes in size. Imagine two arrays, each one being a petabyte of data, and you're multiplying it together. Well, if you write the algorithm to do this, the way that most people do and learn in algebra, you see each element of the array being brought into the CPU, but in the other array, you go down the columns. In the first array, every element being fetched comes out of the cache. In this second array, every single element that is fetched from the array has a cache miss and goes all the way out to the main memory. This slows down the whole multiplication. But in algebra, you also know if you invert the second array, do your multiplication, and invert the answer, you get the same result. So when you invert the second array, every element fetched comes out of the cache, and the entire multiplication happens 40 times faster. 40 times faster. 4,000% faster. Because you know how the computer works. And tapes. Tapes are the slowest thing on the face of the earth. If you don't understand how they work, your program could take hours instead of seconds. You have to understand that there's real hardware out there, even if you're using virtual machines. Now today, a lot of college students are learning Microsoft Office and Oracle instead of learning database theory and structures. Now, I have nothing wrong. There's nothing wrong with a student learning Microsoft Office. And there's nothing wrong with a student learning Oracle. But what they should be learning is database with Oracle as an example of that. And they should be learning how to use an Office package to run your company with Microsoft as an example of that. And OpenOffice as an example of that. And KOffice as an example of that. And MySQL and Postgres as examples of databases. Because then the student can make a decision as to what is the right tool for the job. And when Oracle comes out with the next version of Oracle database, they can adapt to that. When Microsoft adds a new feature to Microsoft Office, they will know how to use it. This is what should be taught by universities, not a specific product. High school students, a lot of times, buy a computer, go down and buy a game, put the game on the computer and play it. They write a little bit of HTML and they think they know how to program. So that most high school students see computers like this, when in reality, computers are like that. And this is why the people at the University of Cambridge decided to create the Raspberry Pi. Because they were getting students coming from high school that knew less about how a computer worked than 20 years before. 20 years before, you got a Commodore 64, or you got an Amiga, and you went to the web, or the internet at those days, a bulletin board, and you pulled down a program that you had to type in. And sometimes you got a syntax error, and you had to fix it. And you learned that way. And you assembled your own computers. And this is what they learned 20 years ago. But today, the students didn't have the same knowledge. And so they created the Raspberry Pi, a $35 computer that they purposely did not put in a case. They purposely left the case off because they wanted the students to see what the Raspberry Pi looked like. I had a friend of mine who ran a programming company. He hired a student right out of university. He was talking to the student and said something about cache. And the student says, "Oh yeah, somehow that makes the computer run faster." This is not the answer he was looking for. And this is a problem with some students coming out of university. Not all, but some. And that's a problem. So here's the Raspberry Pi, $35, single core ARM computer, RISC instruction set, 700 megahertz, which you can overclock perhaps to 800 or so. A 3D GPU, very nice little computer. And this is a fine computer for somebody who's in high school. But you could look at all these other little computers. And each one of them has a specialty that makes it unique. For example, this one over here in the corner has 2 chips on it. Each one has 4 cores. One of them runs at low power, a little slower. It's called the little chip. The other one is a much faster chip, but uses more energy. So you tend to run your operating system here when it has no load on it. And then when you start to have a load, you put the applications over there on the faster chip, which uses more electrical power. And when your processes stop running, you turn that chip off to save electrical power. Here's another interesting chip. This is called the Parallella board. It is $99, but it has a 2-core ARM processor on it and also a field programmable gate array. Now, for those of you who do not know what a field programmable gate array is, when you execute instructions on an Intel processor, the instructions are set up to be a particular way. You cannot change the instructions. Every clock cycle, there's another instruction which you execute. So your program is limited by the speed of the clock and what the instructions allow you to do. In a field programmable gate array, You first tell the circuitry what you want the instructions to be. And you formulate those instructions inside of the gate array, and then you put your data into it. And it can execute certain types of programs 10, 50, or 100 times faster than a regular clock-based CPU. But they're very small programs. So what are they used for? Encryption, or digital signal processing, or being able to do 3D algorithms of different types, or analysis of digital signals coming in. These are the things a field programmable gate array can do if you know how to program them. It also has some digital signal processing chips on there. So you can make your own codec for doing video work or audio work. But it also has a little chip right there which has 16, either 16 or 64 cores to it, where each core has 32 kilobytes of memory associated with only that core. So you could do massively parallel programming with this board that only costs $99 and only uses 5 watts of electricity. This is the type of board that I would like to see university students using. You know, it's fine that high school students use the apple pie, or even first-year university students using it. But as you go up, you should be looking at this type of chip to practice your skills for the 21st century. Now, believe it or not, Linux has actually been around since 1991. So Linux has been 23 years old. But the GNU project started in 1984. And there's parts of that are 30 years old. And actually, GNU was based on Unix, which started in 1969. And so there's parts of Unix which were designed for a computer that only had 64K of memory in its address space. And back in those days, a lot of the operating system was written in assembly language. Particularly in the early days of Linux, a lot of the pieces of Linux were written in assembly language because the GNU compilers were not that great at doing optimization. And if you used a GNU compiler instead of a commercial compiler, you might lose 30% of your performance. So a lot of people would write certain specific parts of GNU in assembler. And then as GNU was ported from architecture to architecture, from ARM, or from Intel to ARM to Motorola, people would take that assembly language and just transport it into the assembly language of the new machine. And this is a very inefficient way of writing assembly language. So we have to remember that in the meantime, memories have gotten larger. We're no longer paying 128,000 US dollars per megabyte. CPUs have gotten multi-core. The GNU compilers have gotten much better. In fact, it's very difficult to write assembly language to be more efficient than what the GNU compiler will generate. Algorithms have changed. Back in the early days of Linux, it was a single-threaded kernel. It was not symmetrical multiprocessing. It had no mmap. It had no asynchronous I/O. It was not a multi-threaded kernel. And so people wrote applications that only used those interfaces. But it's not 1991 anymore. And what we can do is optimize this code to make it better and faster and use less electricity. So today, and I really mean today, I am announcing Maddog and Linero's contest for the optimization of GNU Linux. Because we have found that there are 1,400 modules in GNU Linux which have assembly language in them. And we know that in order for ARM's new 64-bit processor to be able to run GNU Linux, somebody has to port this code. But porting is a very dull and boring job. And there's no glory in porting code. So what we're doing is offering people prizes for the people that can port the code. Sometimes the prizes are simple, like a nice t-shirt. But as you port more and more programs, you get better and better prizes. But we also started to take a look at this and said maybe we should be optimizing this code, making it run better. And not just better on ARM, but also better on Intel, better on Motorola, better on all of the different processors. And we might be able to get 20 or 30% better efficiency out of this code just by looking at these ancient programs and moving them forward. So the goals of the contest are to make sure that all 1,400 of these programs work on a new ARM 64-bit processor, but also to try and get rid, as much as possible, of these assembly language in the code, to move it over to more modern programming using modern-day compilers, and also to be able to increase the performance across all of the architectures. In fact, we do not want somebody to make it run faster in ARM at the detriment of Intel or AMD. That is not a win for the community. And we also want to take this material about performance improvements and algorithms and make a course that can be taught at universities on how to write good performing code. The categories of performance are a percent of speed up of wall clock time, that's obvious, but also memory utilization, because a lot of GNU Linux is also used in embedded products. And we don't want you to speed up the code, but make it gigantic so it doesn't fit inside of small systems anymore. We want to have cache utilization, because different CPUs have different amounts of cache. You need to make the code sensitive to that. A better algorithm placement. And in certain cases, we want to get away from specialized programming in the program and allow this to be done by the compiler itself. These are known as compiler intrinsics. And you'll be working with the compiler writers to determine what intrinsics are needed. We also want to have compiler performance improvements. And finally, we're looking for more categories that we can have in the contest. Suggested prizes, again, just for entering the contest, just for porting one application, you'll get an awesome Linero t-shirt, much like the one I'm wearing. But as you port more and more processes, you will get more and more awards. And every once in a while, you may get a very nice microprocessor like the one I showed earlier. We're also taking every single port you do and putting it into a pool. And twice a year, Linero has a conference called Connect. One Connect is held in the United States, and the other Connect is held in Asia. 2 times a year, we will pull a name out of that pool, and that person will get an all-expense paid trip to the Connect meeting, a week-long meeting to meet with other engineers who are extremely good, to talk with them, to talk about your issues of porting and things like that, and to experience that culture. In addition to that, if you do your porting work soon, right away, you'll be able to be drawn over a 2-year span of time. So you'll get 4 drawings to come through, 4 chances to go to a Connect meeting for every single module that you do. If you do 10 modules, you get 40 chances. If you do your work late, you may only get 2 chances, so that's 20. You'll get half the chances. But we're also giving awards for the performance side. And if you get the best performing, the best increase in performance, you will automatically get that trip to Connect. And we will have a panel of judges to judge that performance increase. Now, there are also side effects of this. Even if you don't win anything, you'll be able to put this on your resume. I took this module of GNU Linux and I made it run 20% faster. I worked with the people who were in charge of this. I interacted with them. It's a piece of the operating system that you, Mr. Customer, use every day. I made that run faster. This has got to be a good thing to put on your resume. And because it's open source, that person can go back to the mailing list and they can see your interaction with the people who are in charge of that module. So this is a very good thing for students who are looking for that first job. You can also learn different coding and analysis techniques and discuss them through forums on our website. And we're looking to turn this into a university course in optimization. We're also looking for mentors, senior engineers and university professors who would like to guide their class in doing this. I had one university professor say to me, Maddog, I make up these tiny little stupid programs for my students to learn assembly language programming. I would much rather have them do this and do something that's useful and do something which is real world than make up these stupid examples. And so he used my contest to be able to give classwork to his students. Now, if you do the assembly language port, what we would like to know is what set of tools did you use to do your work, and what type of problems did you have, and what optimization switches did you use on the compiler. And these are relatively simple things to do. But if you're doing an entrance for the performance, we need you to measure the performance of the module before you do the port and also the performance afterwards. So we can measure the percentage of performance improvement in order to give you the prize that you deserve. Now, if you're really interested in this, here are some resources which you can use. You can learn more about the GCC compiler than probably you would ever want to know. You can learn about debuggers and profilers. And this is stuff that's very, very useful to programmers. And you can learn about a very nice instruction set called ARM. And a RISC instruction set used by processors like MIPS and ARM is very nice because for every clock cycle, you execute another instruction. If you write your C code and you generate that many ARM instructions, that might be good, but you change your C code a little bit and you generate that many ARM instruction sets, and that's probably a lot better. It's much easier to see that with a RISC instruction set than with a complicated instruction set. Because with a complicated instruction set, your instructions typically have different clock times. And it's hard to just eyeball them to see whether it's more efficient or less efficient. It doesn't match up one-to-one. Now the time frame for this is right now. We set up our website. You can log in. You can start picking out modules to port. We'll let you pick out a module. If you do not do anything with it for like 3 weeks, we may send you an email and say, are you still working on this? And if not, would you release the module so somebody else could use it? But each person will have one module that they can work on. When you finish that, you can then pick another one. We have examples out there of porting work. We have all the rules of the contest. And we're looking eventually for a university to take this over in about 2 years as an ongoing project of optimization of GNU Linux. So what should you do now? Go out to performance.linaro.org, register for an account, start to look at reading the information. You can use either the ARM performance programs, or you can use QEMU, which is an emulator, to create your ARM 64-bit environment right on your laptop computer. Once you've done that, you can pick a module, bring it down, put it in the emulator, and port it. There are cross-compiling tools that already exist for the ARM 64 processor, and you can use that to port your code. You will also learn to use QEMU or the ARM performance modules, and that's what you can do right now and continue on with the program. So with that, I'll ask if there's any questions or comments. We have a few T-shirts to give away from Movie Star, and we'll ask for some good questions from the audience, and if you ask a good question, you'll probably get a T-shirt. Thank you.
Hola, ¿qué tal? Mi nombre es Juan.
Any questions?
¿Qué hay acerca del problema del hardware? En mi caso, mi computadora en Linux se calienta porque el hardware no es compatible con Linux.
So I can't hear a word you're saying.
He's asking about hardware compatibility. His computer heats up with software, so he just want to know what's the working with that.
Well, I mean, your computer can heat up for lots of different reasons, okay? And most of the time, if your computer is really heating up a lot, it's probably because you might have your fan might be plugged with dirt, and you better, unplug it, otherwise your CPU would burn up. But, I mean, you can go into the kernel, and in the kernel, in a lot of laptops, not all of them, they have a sensor for the CPU. If the CPU gets too hot, the computer turns back the clock on the CPU. It makes your computer run a little bit slower, but it's better than your CPU heating up and burning up, okay? So you may want to check to see if your particular CPU on your computer has that capability, and then set it so that it turns back if it gets too hot. Did I answer your question? Okay, he gets a shirt. Next, okay, out there, I saw.
Hello.
Hi, and thank you for your presentation. My question is about how do you think, do you think is the best way to introduce a new person to programming? Because as you say, high school students are learning in the bad way, but this way is more familiar, easy for them, and you present the Raspberry Pi as an option for them to learn to program, but that seems kind of hard for them. I mean, they don't see something interesting in that because it looks hard. So what do you think that is the best way to introduce a new person to programming?
I think the best way, particularly with a Linux system, to introduce a student to programming is through shell script. Okay, shell exists on every Linux system. And you can find a book on how to write shell scripts. And with shell scripts, you can have a file with information that's useful to the person and use the shell commands to manipulate that data and to be able to have them do useful things. So I think that shell scripting is the first step. And it's easily done with a text editor, or even you can practice typing in the commands on the command line to see what they do step by step. So that's what I recommend as a first language. Now after that, there's a wide variety of different languages that people recommend, but I tend to recommend Python. Some people say they don't like Python, fine. But I recommend Python because it's a relatively simple language. And again, there's lots of books and tutorials that teach you how to program in it. In fact, there's some online tutorials for free that are interactive that allow you to program in Python. And Python's a very powerful language. You could do a lot of things. After that, I might say to somebody who's interested in programming, learn assembler language. And if you learn assembler language, you can learn it with something like QEMU, or you can program assembly language directly on your computer. It's okay. But then you know how one assembly language works. And you understand more about how the machine works. Then you go in to learn a language like C. Because now you understand what a register is with C, what a pointer is with C, what an array really is. And after that, you go on to learn anything. So that's my recommendation of the order. Is this going to take some time? Yes. Does everybody in the world have to learn how to be a programmer? No. But I think that everybody in the world should write at least one simple program, because then they have an understanding of what the machine can do versus what it can't do. There's no magic. The machine is not intelligent. It's actually one of the stupidest devices you're ever going to meet. They need to know that. That way, when they come to you and say, I want this simple program written, and you look at it and go, that program is going to take me like 7 years to write. They'll have an understanding of why it will take that long. Okay? Next question.
Hello. Thank you very much for your
right here
presentation. In front. Sir?
Or someplace.
I'm here.
Where?
Here.
Wave your hand.
Here.
Where are you? Oh, over there. Okay.
Thank you very much for your presentation. I have a small question about making performance. I am not a programmer, but if I use Linux. So my question is, if you want to learn about reading code and make better performance, do you recommend some distro, or you need to play with Linux from scratch?
Well, there's a variety of different distributions you could use. In this particular case, if you're really working with performance, I would recommend the ARC distribution, where everything is kind of built from scratch from the beginning. The thing is, you're also running this on a virtual machine, either QEMU, or if you're doing the ARM 64-bit work, you're working on a virtual machine. So it's going to be harder to measure exact timings of the virtual machine. Eventually, we're going to have 64-bit ARM hardware up on the internet, and you'll be able to log into the internet and test your programs on that. But that hardware is not available yet. The emulators are perfectly good for doing the porting work and doing the beginnings of the performance work. But the performance work could also be done with Intel or with AMD or with any other currently supported architecture, and then test it out when the ARM64 comes into being. Because again, most of this performance work is going to be across all the different distributions, all the different architectures. So you'd be able to measure the percentage change no matter which distribution you had, no matter which architecture. It's just that the difference performance might change slightly whether you're using a 32-bit machine or a 64-bit machine. Okay? So just get started and you'll work your way into this. Did I answer your question? Shake your head yes or no. He's not shaking his head either way. Okay, I think I answered it. I think he gets a T-shirt. The guy out there in the blue shirt with the big haircut. Or maybe you could come down here to this lady and get your T-shirt. Yes, sir. You have a microphone. Where? Oh, no, there's a person over here.
Yeah, hello. Is there something specific that you would recommend to every programmer out there that wants to learn to optimize his or her own code?
Yes, actually, what I recommend to people to want to optimize their own code is to look at code that is written by very good programmers. There was a man many years ago, his name was John Lyons. He was a professor at the University of New South Wales. And he believed that the best way of teaching people how to write good code was to let them read the code of other good programmers. And so he took the Unix kernel, written by Ken Thompson and Dennis Ritchie and a bunch of other people, and he wrote comments on every single line. And he wrote a commentary about how the kernel worked. And he had these 2 books that he published. And students would read those books and understand why different algorithms were used in the kernel of Unix. How to write your code to be very efficient. It really is the best way to become a really good programmer. And if you want, one of the things that everybody should do is pick out an application or a project that you're passionate about. Do you love music? If you love music, then pick out one of the music applications of Linux and work on that project. Join that team. The first thing you do is you go to the bug list and you find bugs in the software and you fix them. And you'll work with the team to fix that bug. You'll make your code blend into their code. After a while, they'll start to recognize you as a good programmer. And they will then bring you into the development side of the application, not just fixing bugs. This is the way you build a portfolio of programming, so when you go out to find a job, you can point to the fact, I worked on this application, I did this work. But it's also something that you're passionate about, that you want to see successful. So that's what I recommend to most programmers who are starting off, that after they gain a certain amount of expertise in writing programs, that they join a project and they contribute to that project to increase the programming skills. To answer your question. Great. You want a T-shirt? Come down here and get one.
Hi.
This guy, he's got to get a microphone. Okay. The microphone goes to him next, okay? He's very patient. Yes, ma'am.
Hi. Just a little question.
I can't hear a word you're saying.
Do you hear me?
Just barely.
Okay. Just a little question. In your opinion, which and why is most important to perform? The devices that we are carrying with us, or the applications and the systems that are in the cloud that provide information to these devices?
I didn't understand that. Can you somebody help me with because the noise is. Come here.
Okay. In your opinion, which are more
I think the
important
microphone is on. We should say bad things
to
about Google and
perform?
stuff.
Which is more important to perform? The devices that we are carrying with us, or the
Probably
applications
would
that
hear
are
more
in
without
the
the microphone now.
Okay, I think I got it now. She's asking which are more important to optimize, the applications that go on your cell phone or maybe on your notebook,
I don't
or
know
the
how
things
you
that are
can
in the
hold on to
cloud.
yourself.
The
Those
answer
shoes are
is
so
both.
sexy.
But what you're looking for is the smallest number of instructions that are necessary to do whatever task you're doing. That's typically going to give you the best efficiency and also the best power savings, okay? Which are both necessary for the cloud. However, the cloud has one big difference. The machines that are used in the cloud typically have 16 gigabytes, 64 gigabytes of main memory. The processors used on the servers in the cloud typically have a huge amount of cache in the processor. On your cell phone, you don't have the 64 gigabytes of memory.
It's a mobile.
And the processors typically have a smaller cache. So when you optimize for your program, you should think about that. The thing that's probably the most to think about is how much main memory are you using in your program or in your algorithm to get you the efficiency you're looking for. And you may choose two algorithms inside of the module, one for large memory and one for small memory. In calculating sines, cosines, and things like that, there's basically two ways you could do it. You could do it through pure calculation of the CPU, which uses a small amount of memory but a longer period of time, or you can supply a table which gives you gets you very close to the answer, and then have a small amount of computation to get the rest. The table uses up more memory. It's a trade-off. And so you have to make the trade-off given where it's going to go.
Also, I don't know if
And this is one reason why Arch Linux has
was like a
an
pat down by a
advantage,
TSA guy.
because you can compile the whole operating system exactly
Wait, the
for the
microphone doesn't go there?
architecture and the situation you have. The disadvantage of that is if you take that compilation and put it on a different style of machine, your performance isn't going to be the same. Okay. Next question. No, finally.
How can we determine about an optimal level between performance and low power consumption? Or we should sacrifice power consumption in order to get a better performance, or vice versa?
Well, actually, that was the
I have
same
to set up my
question you
computer
just
soon.
asked.
Yeah, I know.
And the answer is, typically, the fewer
leave
instructions
it
you
there.
have to
Leave it there.
execute
I have to
in
get my
order
cables
to
and
get
everything.
the project done, the program done, the less power performance, the power consumption you're going to have. So one of the things around power consumption is, how fast can I do the task, get the task done, so that my operating system can now quiesce so that I don't use as much battery. The same situation happens on the server, because if the process on the server finishes, then the operating system can turn off memory. The operating system can shut down disks. The operating system can do all these things to save power. So what you want is the smallest number of instructions and the least amount of memory to be able to do what you want to do.
Yeah.
Unfortunately, these sometimes come into conflict.
Magic.
The amount of memory you use versus the number of instructions. And that's where we had a discussion about the trade-off.
Holds
What should
cup drops.
be the
Yeah.
priority?
There you go.
What we should focus more on performance, on power consumption?
It's always on.
If you have to choose between one of those, what will be the performance? Should be the first option to get it?
No, performance is always going to be more towards power consumption. But it's how much memory do you use, or how much CPU cycles do you use? Or do you even use a coprocessor that gets around the whole problem in the first place? These are other things. When you get into the performance side of the contest, it's not a simple yes or no. It's going to be something that people will have to judge to figure out what's the best answer. Okay? And this is why you also have to go back and work with the people who own that module, who own that program in the GNU Linux model, because they've worked on this a long time. And you need to talk to them first about your ideas of what you want to do so they can say, yes, that makes sense, or no, that doesn't, and here's why. Okay, so don't just spend a lot of time on the module and then toss it at them. What you should, and on our site, we talk about this. You talk to them first, tell them what you're doing, and then that you get feedback from them as to what the best thing to do is. Okay? Because they will give you guidance whether you should use more memory or less to get the performance you're looking for. Okay? I can't answer the question absolutely, because there is no absolute. Oh, we're out of time. I want to thank you very much for coming. I hope that you all enjoy the contest. Thank you.